All right, we want to talk about the mean and the standard deviation of a binomial random variable. But first, we're going to talk about how you can do this stuff even more efficiently on your calculator. Okay, so you're given some context, right? There is the number of trials that you're doing, and that'll be used here, and the probability of success, right? Because if you think of bins, the number is fixed, that's my n. The same probability of success, that's my p, and we're looking for a specific number of them, all right? A number of successes. So whatever context you have, you can imagine this situation. Mr. Cran's 80% free throw shooter. What is the probability he would make only 5 of 10 free throws? So the most he could make is 10. We're wondering that's not the probability. The most he could make is 10. And we're wondering what's the probability that he makes 5 out of 10. All right. We could find the probability that he makes 5 or fewer, exactly 5, 8 or more, right? We can calculate lots of probabilities in this. So on your calculator, there's an option for Binomial PDF, and it'll ask you for your n, the number of things in your sample, okay? Number in sample. Hopefully you know what the p is. This is your probability of success. And you're going to want to write that as a decimal, so 0.0p. And this is the k that you're asked about in the particular problem, okay? This is the number that you're measuring. So this is the probability that x equals k, all right? This will always calculate for you. This is the probability distribution function, and it tells you exactly what that probability is in that one little box. This one tells you the probability that x is cumulative distribution function less than or equal to k. And so this one will give you, nope, wrong one. I want to do a highlighter. Here we go. So this will do all these boxes added together. Okay? So probability density function, PDF, will just fill in a single box. CDF will fill in that box and everything below it. All right, so let's try and answer a few of these questions. If we want the probability that Mr. Kranz would make only or exactly, how about we say that? Exactly, make it clear what I'm looking for, 5 out of 10. Then I would have to do Binomial PDF. So I'll just write Binomial PDF, and I'm taking 10 shots. Probability is 0.8, and I'm going to make exactly 5. Okay? So on my calculator, I can come here and say second distribution. If you go up, Binomial PDF and CDF, it's easier to get there going up than it is down. Okay, Binomial PDF, 10 trials, probability of success is 0.8, and I'm going to get exactly 5 correct. Okay, so there's my n, my p, and my k, and it comes out like that, and we get 2.6% chance, okay? 0.026, and this is the probability that Mr. Kranz makes exactly 5. Now, how about this? What's the probability that he make 5 or fewer? So this is the probability that x is less than or equal to 5. And in this case, I'm going to do Binomial CDF because I want to 5 or fewer, I want to accumulate all of them. And so it would be 10.8, still 5, because it'll do 5 or fewer. And this time, same spot, second distribution, go up. We can do Binomial CDF, 10.8, and 5. Enter. 3.27, or 0.0327. Okay? How about this last one? That he would make more than 8. So here, I'm just going to sketch in my diagram here. More than 8 means that we want this probability. Oh, not that probability. We want these two probabilities. If we want more than 8, we want those two. So I could do a PDF of 9 and a PDF of 10 and add them together. Or I could use a CDF by calculating all of these and subtracting from 1. Okay, so if I want more than 8, probability that x is greater than 8 is the same as 1 minus the probability of x being less than or equal to 8. which is 1 minus binom CDF of 10.88. Okay? And if I grab my calculator, 1 minus second distribution up a few times, binom CDF, 10.88. And I get 0.376. Okay? So that is the calculator. The PDF function fills in a single box. The CDF function fills in that box K and below. Okay? This is everything K and below. The other thing I want to talk about is the mean and the standard deviation. All right. So if X has a binomial distribution with a number of observations N, probability of success P, the mean and standard deviation R. So if I flip a coin 30 times, my N is 30. My probability of rolling a 1 is 1 out of 6. So if I roll it 30 times, I would expect 5 of each. The number 30 times 1/6 gets me that 5. Okay. The standard deviation comes out to the square root of N times P times the number of failures, 1 minus P. Okay. I'm not going to get totally into the derivation of those right now, but I might mention it a little bit more detail in class. But the square root of NPQ, right? This is also known as Q, 1 minus P. I'm going to use them both, so I want you to be familiar with both. So there was an example of bad switches earlier where you have a sample size of 10, probability of 0.1. This is the sampling distribution the engineer would see if they drew all possible simple random samples of size 10, right? You could have 10 failures, but you're most likely to have like 0 failures or 1 failure, maybe 2, maybe 3, maybe 4, maybe 5, maybe 6. But it's really going to shrink down. And all of these probabilities would have to add up to 1. Okay, that's my sampling distribution. What would be the mean and the standard deviation? The mean needs to be the balance point of this. All right, and it would be mu equals, my N is 10 times 0.1 equals 1. And my sigma would be the square root of 10 times 0.1 times 1 minus 0.1, which comes out to square root of really 10 times 0.1 is 1 times 0.9, so we get 0.95-ish. Okay, and that means that in the long run, I would expect to find an average of one failure. All right, and my average distance from that mean is 0.95. So I'm just as likely to have 0.05 as I am to have 1.95, right? So like on average, how much would I be off by in the long run? These are long run calculations. All right, so the mean and standard deviation, binomial random variable, these are super helpful, especially mean and standard deviation get especially helpful when we start doing normal calculations, and we will get to that very soon. See you later.